our mini series on factors of IID. So Omer is speaking for us today on the loop O1 as a factor of IID.
Yes, thank you, and thanks for the invitation to speak here. So I'm not sure what people's backgrounds are and what people are familiar with, since this is a series. So I want to assume not too much, but if at any point I'm assuming things are known and they are not known, then let me know. Also, if I'm saying things that that everyone is familiar with and they should go a bit faster, let me know. So I'm going to talk about some recent joint work with Gura Bray and Dinon Spinka about understanding the loop O1 model as a factor of IID. And let me start with a brief okay, so maybe so actually, given that this is a series, so is there a need to define factors and at all, or can we assume everyone is?
I think you don't need to define them, but maybe I'm not the best person to say that.
Okay, so I'll just go over this fairly quickly, just to set things clear. So we have some process X. So we have X is some process on some graph G, and the graph G could be ZD or Z, but it could also be other things. We are interested in fairly general setting today. And then we say we have another process Y, which is also on G. So Y is a factor of X. If you can write that Y is equal to some function phi of X, where the function phi has to be measurable, first of all. And the function phi needs to be equivariant. So if you apply some automorphism of the graph and translate all the values of X and then apply phi, then everything is translated. The values of Y are also translated. So that's a factor of IID. And again, assume people are familiar with this notion and understanding which so that's factors, and especially interesting for us are factors of IID. So Y is a factor of IID. So IID. If there exists some process X, which is just a process of IID variables, and Y is a factor of X. So that's the factor. So at least on ZD understanding, so every process can be written as a factor of IID, and if you can also achieve the entropy. So if you have a process with some finite entropy, then it's in fact isomorphic to an IID process. But on other graphs, things are not as clear cut. So that's.
Omer, I didn't understand things on factors of IID. When you said every process can be written, you were making some assumption. Bernoulli process.
Hello, Yuval. So let me not stick too much on this, since I want to get to the more interesting. Okay, but on ZD and general understanding, factors are relatively well understood. So we know. So there is a second notion that is much more mysterious, perhaps, which is finitary factors. Which, and in the case of IID, we will denote it FFIID, so a finitary factor of IID. And the process is a finitary factor of IID if the function can be determined by some random, by looking only at a finite sample of X. So the precise statement will be that So y is a finitary factor of x. If there is also some random r, so there exists some, well, it doesn't have to be random, it's allowed to be random r, such that phi of x is determined by x restricted to the ball of radius r. So if you look, so you have some vertex, some vectors rho, and if I just see the values of x on some finite radius, then this is enough to determine the values of r. And you can think of this like a stopping time, that you start looking at the vertices of x incrementally, and at some point you say, I've seen enough and I know what is the value of y. So the simplest examples of this are block factors, where you have a constant r, so y at a point is just some fixed function. For example, you might take the maximum of the process x over the ball of radius r. But there are things, but there are examples that are not that are finitary but not block factors. And an example, a nice example that you can keep in mind for this. So let's start with percolation, with critical percolation. So does everyone here know what Bernoulli percolation is and the basic properties, or should I?
Yes, everyone knows.
Okay, so so suppose X is just a Bernoulli percolation. It could be bond or site, doesn't really matter. So say the edges are open or closed. And now we can consider the process Y, which assigns a random bit to each cluster. So Y, so you have a random, let's say plus or minus 1 on each cluster. So the process X itself is IID. So the percolation is by definition just all independent. But then you might ask, well, is y a factor of IID? Is it a finitary factor of IID? So if you have no infinite cluster, so if X has no infinite cluster, then y is a finitary factor of IID. This is and the reason for this, so you need to say, so the process, the IID process is not only X, but you need some additional randomness. So for example, you can say that, so let's imagine we are doing this on ZD, though it doesn't really matter what graph this is on. So suppose that every vertex, apart from the bit telling you whether it's open or closed, you also have a bit which is plus or minus 1. And then when you have a cluster, you just, the whole cluster takes the bit, for example, from the lowest leftmost, or the minimal vertex in some order of ZD. And okay, so you might say this is not invariant to rotations of ZD. You can also find this as a factor. There are other ways to break the ties to make this into a factor. So there are many ways of doing this. And if the clusters are all finite, then this is the finitary factor of IID. What happens if you have infinite clusters? So if X has a unique infinite cluster, then Y is actually not even ergodic, because the unique infinite cluster will have either be all plus or all minus, and so you'll have a non-trivial density for a bias on the density between pluses and minus. So Y is not ergodic, so it's certainly not going to be a factor of IID. So it's not a factor of IID, never mind finitary. And if you have infinitely many infinite clusters, then this is actually then this is not so clear anymore. So so you have So you can, and there are several cases you can think of. For example, if you look at a regular tree, then you can have infinitely many infinite clusters, and that's an interesting question. But just to highlight the difference between factors and finitary factors, suppose you have unique infinite clusters, but you say that the infinite cluster, you always take the plus sign on that. So so you don't, so now this is ergodic. So let's say go back to the unique case. So if infinite cluster is always plus, then this is ergodic, and it is still a finitary, it's still a factor of IID. So you can do the finite clusters the same as before, and the infinite cluster is just plus, but now this is no longer finitary. So this is a factor of IID, but well, it's not clear, it's not obvious that it's not finitary, but at least the description that I gave you does not give a finitary factor, because you cannot, if you reveal X, you can never say that you are definitely in the infinite cluster. So there's always some chance that you're in a very large finite cluster. So so that's a very brief review of factors and finitary factors. And I'll okay, and now a second question. So to what extent are people here familiar with Ising and Lupo-1 models? Ising, FK Ising, Lupo-1. So I know that Alan gave a talk in this a couple of weeks ago. So but I don't know if everyone was present at Alan's talk.
I think you could maybe give a brief overview of the Ising model, but we haven't talked about Lupo-1 at all.
Okay. Okay, so that's what we do. So the Ising model, and essentially just to set the notation. So the Ising model. So if you have some configuration sigma, which is in ±1 to the vertices of the graph. So here are the vertices of the graph, and on a finite graph. So if G is finite, then you can take the probability of configuration sigma. You can take it to be well, proportional to e to the beta times the sum of sigma x sigma y, where you take the sum over all adjacent pairs x adjacent to y. So you have so beta is the inverse temperature, a parameter. So that's so that defines a measure for every beta on a finite graph, and then you can take infinite volume limits of this. So and these limits are known to exist. So you have so you can talk about mu plus or mu minus. So these are the limits if you put plus or minus boundary conditions. So you truncate the graph and put either plus or minus outside, or you can take free boundary conditions. So these are plus, minus, and free boundaries conditions. And so so these things exist. In the case of ZD, or the amenable case, the free boundary condition, the free measure is just a mixture of the plus and minus boundary conditions. And again, just some key fact is that there is a critical transition. So there is a phase transition where for large beta you get non-uniqueness. So mu plus and mu minus are different, whereas for small beta you get a unique. So all of these measures will be equal. And this can be related to factors of IID, but so there is a result of Ornstein and Weiss. and then of Adams. So also I believe Onsen and Weiss was just in ZD, and Adams wrote this in detail also for the amenable case, which says that on an amenable graph, mu plus is a factor of IID for every beta. And so that's for every beta, and this has been extended recently also by RL and Spinka for more general models. So there is a class of monotone models where the interactions are monotone. So you have so the Ising model, if you have more pluses, it only increases the probability of pluses elsewhere you have positive correlations, and you can do this with more than 2 spins also. So so you have this property, and this is essentially by arguing that the Glauber dynamics can be used to construct a factor, to construct the stationary measure as a, or the limit measure as a factor of IID. But for finite factors of IID, it turns out that there is a more interesting picture, and this was highlighted by Vandenberg and Steiff. So there's a result in 99 that mu plus, this is again in the amenable case, mu plus is a finitary factor of IID if and only if you have uniqueness, if and only if mu plus is equal to mu minus. So in particular, if you have a high beta, then it is no longer a finitary factor of IID. And roughly speaking, the idea for that is that finitary factors of IID always have exponential rates for large deviations. So if you look at a large ball and you ask what's the probability that this large ball is predominantly minus, so if you have any finitary factor of IID, so if you have any finitary factor of IID, then the probability that the entire thing is predominantly plus, but in a ball of radius r you are predominantly minus, decays exponentially in the volume.
Omer,
yes?
didn't Vandenberg Steiff leave the critical case open? I don't think so. So they showed that if beta is below beta c, then it's finitary factor of IID. But
so
at beta, didn't resolve it.
So if so you're saying if at criticality mu plus, so yeah, it might be. I'm not. Yeah, I haven't looked at it recently, but just to finish what I was saying. So if you look at the Ising model, if you have a very large ball and you want this ball to have predominantly minuses, then you can do this. The probability of this decays only exponentially in the boundary of the ball. Since if you flip everything in the ball, the probability changes by a factor which depends on the size of the boundary, which is sub-exponential in ZD or any amenable graph. So if you are at criticality and mu plus is not equal to mu minus, then
if it's equal.
Okay, if it is equal,
which it is equal. You know,
yeah, it is equal. So
yeah. So
yeah, okay. So and if it is equal, then doesn't the Glauber dynamics still give you this that it's a factor? Okay, so that doesn't give you the finitary factor. Yes.
No.
Yes, you are right. So yes, you're right. I was mainly thinking about this as being the obstruction to being a finitary factor, but in the critical case, yeah. So
their paper, they didn't settle the critical case.
Okay, and is this? Do you know? Is this still open? Or?
So I missed, but didn't Spinka talk about this again? I missed Spinka's talk, but
Okay.
So
Okay, so I'm not. Yeah, so I'm not 100% sure then about the status of the critical case, but yeah. So let me also mention. So things are also very interesting in the case of trees. So with these results, well, possibly except for the critical case, we know what happens on amenable graphs. On the trees, things are are even more mysterious, and I'll just and again there was a talk by Alan Sly in this seminar a couple of weeks ago on exactly this, but so on trees, so on trees it turns out that the free measure, so mu plus is still a finite, is still a factor of IID for all beta, and it's a finite factor if it's equal to mu minus. And sometimes it's a finite factor also for large beta. So okay, so I won't write all of these things down, but the free measure. So the free measure, it turns out, so there is a phase of small beta where it is a factor of IID. This is the result of Nam, Sly, and Zhang. I guess that's what Alan was talking about. And it is not if beta is large enough, and there is some gap where it is not where it is still open. So on trees, UF as a factor of IID is partly open. So it's known that there are phases on both sides, and the transition does not seem to be with the uniqueness at the uniqueness transition, but that's okay. So that's the Ising model. Now there is a closely related model I should mention, the Ising gradient, and the gradient Ising. So the gradient Ising is also you just look at which vertices are nearby and which are equal and which are not, and this exactly eliminates this obstacle that we had with the for the Ising model to be a finite factor of IID. So let me just denote this. So the gradient Ising, you just have an environment on the edges. So you just define that the gradient sigma on an edge xy is just the product sigma x sigma y. So you know for each edge whether it's equal or not. And this model is not monotone. So you can't use some of the tools that are all for general monotone models. However, there is a theorem. So there is a theorem of Ray and Spinka saying that on ZD, that grade Ising is a finite factor of IID on ZD at any beta. So even if you have a non-uniqueness, then the gradient is a finite factor of IID, which shows that this large deviation obstacle is the only thing that's preventing this from being a finite factor of IID. So that's So that's what I want to say about the Ising model. And now moving to the Lupo-1 and the FK Ising, which are two closely related models. So I start with the FK Ising, which is the relation to Ising is is fairly straightforward. So again, on the finite graph, you can define it. So if G finite, then you can define that the probability of a configuration omega. So this is so the configuration here are on edges. So it's 0, 1 to the edges. So we have open and closed edges, and the probability of configuration omega is going to be proportional. So up to normalization, we have some weight p to the number of open edges in omega. So is open edges, and then we have 1 minus p for each closed edges. And then you have a factor 2 to the clusters of omega. So k is the number of clusters. So connected clusters. So on a finite graph, this gives you a measure, and you can generally replace the 2 by a general Q, which gives things related to the Potts model. So that's what you do on a finite graph, and you can again take free and wired limits. Which we denote by phi f and phi w. So those are the free or wired limits. And again, those limits are known to exist. And the key connection is the Edwards-Sokal result that says that if you assign each cluster of this a random spin, plus or minus 1, then you get the Ising. So random spin on each cluster gives the Ising. The Ising measures either the free or the wired accordingly. And this was also, and again, since we are discussing factors of IID, these are also known to be factors of IID by results of Hagstrom, Jonsson, and Lyons. So this is also so those are both factors of IID in general. And okay, so that's so that's the FK Ising. There any questions at this point?
So let me just try and make sure I understand. So you have this FK Ising model, and then
Yes.
if you put a random spin on each cluster, it just becomes the Ising model.
So you
Like
put a
here.
random spin on each cluster and forget about the edges.
And forget about the edges. And
Yes.
so, I mean, the original model is you have spins on vertices, or do you have spins on both vertices and edges? Or
So the FK Ising, you have a configuration on the edges. So you
Oh,
have
I see.
So you have a percolation on the edges where each edge is open or closed, and now you get connected clusters. And on a finite graph, it is a fairly straightforward calculation that if you now assign a random spin plus or minus 1 to each cluster, so each cluster has a single coin determining the spins, then you get Ising.
Oh, okay.
And you can also go back. The reverse connection is also quite simple. If you have the Ising configuration of Ising, so if you have an edge which connects a plus to a minus, you know this edge must be closed since they cannot be in the same cluster. And if you have an edge that connects a plus to a plus or a minus to a minus, it could be either open or closed, and they're all these edges are independent. So you can check that. So you can check that both of these procedures. If you look, you can look at the combined configuration where you have both the spins and the edge open or closed edges, and both of these things give the same measure on this larger space.
Oh, okay, great. Thanks.
Okay, so the final model that we said we introduce is the Lupo-1. So the Lupo-1 model, again, is also closely related to Ising, and the connection is through the FK Ising. And here we have a configuration on open edges and vertices. So we have some configuration, let's call it eta, to stick with my notations. So eta is the configuration on 0, 1 to the edges union vertices. So every edge can be open or closed, every vertex can be open or closed. And we have two parameters, x and y. X is related to the temperature and y is related to the magnetic field in Ising. So we have x and y are positive parameters. Well, so we have two positive parameters, x and y, and well, 0. Yes, can also allow 0. So on a finite graph, we consider percolation. So the idea is that you have a weight x for every open edge and y for every open vertex, but there is a constraint that you're looking at an even configuration. So what is an even configuration? It means that for every vertex, the sum of the adjacent edges plus the value of the vertex has to be even. So for every vertex v, eta of v plus sum overall u adjacent to v of eta of vu has to be even. So so it's 0 mod 2. So that's an even configuration, and there is a picture that you can think that's useful in a lot of these discussions. So if this is the graph G, you can imagine that we have an extra vertex outside, which we call the ghost vertex. And now if you have some configuration, so for example, you can have a configuration where you have some open edges, maybe something like that. Let's do this one. And then you have some additional, you include the edge to the ghost whenever you are otherwise an odd vertex. So we have, so let's actually just draw them in blue. So we have these edges to the ghost are open. So what I've done here, so the red edges are the open edges in the original graph. We have, in this case, 7 open edges and 2 closed edges. The blue edges denote that for this vertex here, for example, eta of v is 1. So we have so eta of v denotes whether the edge to the ghost is open or closed. So this is edge from V to the ghost is open. And now you just ask for this to be an Eulerian graph. So every vertex has even degree. So that's the case. So that's the Lupo-1 model. And a special case that is of particular interest, the simplest case is when x is 1 and y is 0. So if x is 1 and y is 0, well, y equals 0 just means that you do not allow any edges to the ghost. So really you're requiring all the degrees to be even. So this, and x equals 1 means that you don't care how many edges you have. Sorry, I forgot to write down what is the weight. So the probability of a configuration eta, we say we want this to be proportional on a finite graph to x to the number of open edges, x to the open edges, and y to the number of open vertices. And we have the indicator that eta is even. So this is restricted to even configurations. So if X is 1 and Y 0, then effectively you're just taking a uniform even subgraph. Of a given graph G. So that's the Lupo-1 model. And and here again, you can take free and wired limits. So and these things still exist, but it's no longer easy to see that they exist. There's no clear monotonicity that can be used, and actually the existence is proved through the connection with the Ising. And okay, and time is running short, so let me just give the main result that we prove about this. So first of all, for the wired one, we know that it's a factor of IID, and except for one case, unless we have one case, so X needs to be 1, Y needs to be 0, and the graph G needs to be two-ended. So should I say what two-ended means? No?
No.
Okay. Yeah, so the wired one, so this is the only problematic case, and the simplest example of this is if the graph is just the line Z, which has two ends, and on a graph Z, the random even configuration is either everything or nothing. So clearly this is not ergodic, so it's not a factor of IID. And every other case, so if a graph in general is two-ended, then similarly you have some parity constraint, which shows that this is not ergodic. So that's the obstacle. So this is the only possible obstacle. But for the free, things are a bit less clear and not as easy. In some cases. And the conjecture, we believe it's always a factor of IID. But we can prove this. So we can prove this if Y is positive, then we can prove this with no assumptions. We can prove this if the graph G is planar. We can prove this if you have if the graph G does not have too many geodesic cycles. So has finitely many through each edge. So what is a geodesic cycle? A geodesic cycle is just a cycle so that for any 2 points on the cycle, there is no shorter path except going through one of the sides of the cycle. And it's a bit non-obvious how to come up with graphs where this is not the case, where we have infinitely many geodesic cycles. But nonetheless, it is possible. So there are groups, I think sometimes referred to as Gromov monsters, which so you can construct groups which do not have this property. So that's
Omer, to orient us, could you just tell in the case of Z what happens when you go to the free instead of the wired?
So when you go to Z, so if you try to do it, so if you take Z So what is the free limit? You take a finite interval and you take a, so in the case x equals 1 and y equals 0, for example, a random even subgraph of this is just empty always. Since you have an interval, you cannot have any even subgraph of this that is, so in this case, if y is 0, then it actually doesn't matter what x is, then you just have the empty graph.
Okay.
If y is not 0, then you have some collection of segments, and you have a cost for whenever a segment begins or ends, you have a cost of y, and then you have some weight x for every edge that is inside the segment, every edge, and again, if y is non-zero, then it's not hard to show that this has a limit. Then you get some configuration of segments with gaps between them. So.
Okay, thank you.
But yeah, but if y is 0, then you just have always the empty graph. So there's no obstacle here for the free. Whereas for the wired, if you take a z and you take the wired case, so in the wired you can also identify the two ends are identified. So you have either the empty or the full configuration, and you get probability half for each of them. So in the limit you get it with probability half, you get the empty configuration, with probability half you get all of z. So okay, so how do we try to understand this LUPO1 model, and how do we show that that it's a factor of IID? And the main idea is goes through a relation with the FK Ising model. So these are some results from a few years ago of Eisenman, Dubinil-Kopan, and Sidorovicius. So they have a relation between the LUPO1 and the FK Ising model. And the relation, so you have the two parameters P and Q for the FK Ising model, you have the two parameters for the LUPO1. So there's an explicit relation, so P needs to be 2x over 1 plus x, and Q needs to be 2y over 1 plus y. So what is the relation? So they give a way of going from one configuration to the other. So given the loop O1 configuration, so you have some configuration on open edges, open and closed edges, including also the vertices. So to get to the FK Ising, you just need to add Bernoulli configuration. So you just open you additionally open edges independently with probability x. So if you open each edge independently with probability x, and the result turns out to be exactly the FK Ising model. So for the FK Ising model, you don't have the vertices which are open or closed, you just forget about those. So this gives, this is a way to go from the LUPO1 to the FK Ising. And if the other direction is also quite nice, given the FK Ising configuration, you just take a uniform even subgraph. Make uniform even subgraph of the configuration, and this gives us the LUPO1. So so that's so that goes between the two of them. So then the main scheme in order to get the LUPO1 factor, the LUPO1 model as a factor of IID, is to start with the FK Ising model, and this. So here we have the monotonicity. We know that it's a factor of IID, And now I want to take a uniform even subgraph of the FK Ising model. And so the main step that is needed is in order to do this. So FK Ising is a factor of IID. So we need a uniform even subgraph as a factor of that. So there is a question, okay, so how do you take a uniform even subgraph of some given graph? So the graph now is no longer transitive, it is just the FK Ising configuration. So we have just some open edges, some open edges, and we are restricted to them. And we want to take a random even subgraph of that. So the key idea is to look at the cycle space. So the cycle space, so this is the space of all even subgraph. So it's the space spanned by cycles in a graph G. And okay, so you can consider this space over the real, but here we consider it over Z2. So we have just a Z2 algebra and a Z2 vector field, where every edge is either open or closed, and the addition is just edgewise addition, mod 2. And you have this, and so you have the finite cycles which generate some subspace. And this is the cycle space. And again, so on a finite graph, this is again fairly straightforward. But when you want to define this on an infinite graph, again, you can take two limits. So on a finite graph, this is just a subspace. Let's call it E, which is a subspace of Z2 to the edges. On an infinite graph, you can take two different limits. You can take the wired and free limits. And so on an infinite graph, so you have the free limit and the wired even subgraph. So what are these? So the free limit is what is generated by all of the finite cycles. So this is the span of all the finite cycles. So you have every finite cycle, you look at everything that is generated by them. So the wired limit, so this is spanned by cycles plus by infinite rays. So you have, so this is also allowed, and you can, and maybe one small example that shows the difference is the ladder graph. So on the ladder graph, the finite, so the cycles are just generated by the individual squares. So the wired configuration here. So a wired even subgraph will just be a collection of rectangles like that. Whereas for the free one, that's for the free one. For the wired, you're also allowing to take the double infinite path. So if you, for example, take just the top line and you add the top line mod 2 to this configuration, then you'll get a configuration that looks like this. So that's so this is also an even subgraph, but you only get this in the wired limit. So these are the wired and free even subgraphs, and they are related to what is needed to get the wired and free the wired and free loop O1 models. So okay, so how do we take a uniform element in this subspace? So given a basis let's call it BI. For one of those even subgraphs, it could be the wired or the free, depending on what you're doing. You can take just the sum of epsilon I BI, where epsilon I are just 0 or 1 independently. So this is going to give us, so if you have a basis, this gives us a uniform element in the subgraph. This is true for any basis of any vector field over Z2. Well, there's a slight caveat that in order to, for this, when you have an infinite basis, in order for this term to be well defined, we need that every edge is contained only a finite number of the basis elements. So these basis elements are now either cycles or double infinite rays, or they could be other even subgraphs. But this works if for every edge is contained in a finite number of basis elements. And so, so the main thing that is needed is to try to construct a basis for the even subgraph space, which is locally finite, meaning that every edge is contained only a finite number of elements. So, so here's one way of doing this. So suppose I take a spanning tree. So given a spanning tree of a graph G, so you have some tree of a graph G. So here's a way to get a basis for the cycle space. So for every edge that is not in the tree, so this is an edge that is not in the tree, you can complete this edge to a cycle by going through the tree. So this gives us a basis for the elements. And if you have a spanning tree, if it's a connected spanning tree, then this gives us a basis. However, it's not generally locally finite. If the tree has, if you have two paths in the tree that have infinitely many edges connecting them, then this edge could possibly be in infinitely many cycles. So if you have a one-ended spanning tree, though, then this gives us a locally finite basis. So if we have if the tree T is one-ended, you get a locally finite basis. So that's one of the ways, and then you can try to take your favorite one-ended tree, which you can define as a factor of IID. So, for example, in many cases, you can take the uniform spanning tree, which will work. So that's one way to get the basis, and that goes to some of the proofs. And again, I'm really running out of time, so I will not go into too many details. But another way is to take a uniform spanning forest. So if you have a uniform spanning forest, and this is useful for the free case, if you have a uniform spanning forest, then if you have an edge connecting, you take all of the previous cycles, but now if you have an edge that is connecting two different forests, then you need to take a path to infinity along each of those trees and add that to the edge. And this gives us a doubly infinite path.
Omer, you said this is useful for the free case, but you meant this is useful for the wired case.
Yes, sorry, yes. Yes, sorry, I reversed those. So for the wired case, we can take this gives us a basis given a forest of one-ended trees. Well, okay, so the wired spanning tree gives us such a forest in a fairly general setting, in many general settings, and the wired uniform spanning forest is also, for example, on a transitive graph, it can be shown to be a factor of IID by using a version of cycle popping algorithm. So this gives some of these factors. And okay, so I'm really running out of time, so I think maybe I'd not go into more details now, but if there are some questions, I can answer, but otherwise I should stop. So.
Let's thank Omer. Do you have time for a question or two, or do you need to head out?
Well, I told my students I'll be a bit late today, so I have time for a short discussion, but it shouldn't be too late. So yeah, so I should mention, by the way, some. So there are several questions here that we don't know, but I guess one of them. So in general, is when. So how can you get random trees, random spanning trees as factors of IID? So in particular, if you have a transient graph, then the uniform spanning tree. Then the wired uniform spanning tree is a factor of IID by cycle popping, but can you do this on arbitrary recurrent graphs?
On arbitrarily what?
On a recurrent graph.
Oh, on a recurrent graph.
Yes,
I see.
since cycle popping gives a factor on a transient graph, and there are some arguments that work on Z2, but I don't know if this is known for arbitrary recurrent graphs.
But you're talking about getting a tree, not a forest, because
Yes.
On some graphs, there's just no way to get any, any invariant tree.
Yes, you have. Yes, indeed, you have some non-treeable graphs. This is some you and Lyons, is it? Or?
So one example is Pimentel and me, yes, but there are other.
Pimentel, yes.
Well,
Yes, yeah, indeed, there are some non-treeable groups where you can't do this at all. So never mind as a factor, but yeah. But can you do this on as a factor on a recurrent graph?
So recurrent graphs. So it's finite extensions of. But you're talking about recurrent transitive graphs, right?
Well, it could be unimodular also is relevant. So in this context, for example, we want to apply this to the FK Ising clusters, which are unimodular but not transitive.
So how about on like the uniform infinite planar triangulation? So this is known to be recurrent.
Yes, indeed, that's one interesting example of a unimodular recurrent graph, and I don't have an answer for that one. So.
Here's maybe a very general question about finitary factors of IID. In these theorems, can you say much? No, if you do have a finitary factor of IID, can you say much about the covering, about the radius? Or I'm not sure if the radius is really the appropriate thing to study, but about the coding
the radius. Yeah, so it is referred to as the coding radius, and there are some so there are various results about this for finite factors. So there are some results on Z and ZD about things that are possible and not possible, and there are also some fascinating open problems there. So there are some gaps. So you can get so on Z you can get things with the coding radius so you can get things which are bounded, and you can get things which are which have a tower law, and you can get things which decay like a power on ZD. But there's a question: are there actually gaps there? So is there some dichotomy where where there is you're either faster than decays faster than this, or slower than this, or could you get things in between? So those things are quite mysterious. So there are these examples where you have a tower rate of decay for the coding radius, so extremely fast, and I think it's known that you cannot decay faster than that without being a block factor. So there is some gap there, a small gap, but some of the other gaps are still open.
I'm also wondering, like, if there's some, in some cases, it seems like the factor of IID that you get, or the factor map itself, it doesn't depend very much on the graph. That you have a recipe that is very general that seems to work for all graphs. But maybe there's some conditions on the graph, but is this, do you agree with that? Or do you think that you really need to know the graph structure and tailor the map to the graph?
Well, okay, so if you refer to what we were doing here with the even subgraph of FK Ising, then then in the free case we do need to tailor this to the graph in some ways in order to get this locally finite basis. And that's partly the reason. So we had this list of several categories of graphs where we can do things. So for example, in the planar graph, there is a nice collection of cycles. So you can just take, in the planar graph, you can just take the faces as cycles. That's a natural basis for things. And if you have finitely many geodesic cycles, you can take all the geodesic cycles. So if you have any cycle, then it is, if it is not geodesic, then it is spanned by shorter cycles. So
I guess what I'm wondering is whether, in some, I mean, maybe the answer is no, but I guess what I was wondering is, could you define the factor map on the space of rooted networks? Like on the entire space of rooted networks.
Yeah, that's
okay, except for some subset maybe that's like measure 0 with respect to every unimodular measure.
Yes, well, yeah, so that's an interesting idea, though. Yeah, though it's not clear exactly how to formalize this requirement in a way that will make it that will not have some obvious answers. But so I'm sorry, I do really have to get going since I'm supposed to be teaching a class now, and so it's the last class of the semester and it's just a review, but the students should not be waiting. But if Luis or Yuval or anyone else wants to discuss it a bit more, I could be back in an hour, and if so we can discuss by email.
Yeah, let's discuss by email.
We'll write email to you. Thank you.
Okay, so thanks for the invitation, and sorry I can't stay for a longer discussion.
No worries. Thank you.
You're welcome. See you.
Thanks for the talk.
My pleasure.